So this problem we are going to discuss, right? This problem we have, how many of you have done this problem? So what is the flux per pole you found? Can you tell me? Yes. That is 5p. Huh? Okay, what is the area you found? Please tell me. Because this is a two-pole machine, so area per pole you can tell me area per pole. Hmm? Okay. So now you can multiply this with the flux density, which is given 1T, right? 1 into this pi RL into 0.8. So you will find the flux per pole. Okay. So what is the value of flux per pole? Can you tell? This is in centimeter, so we convert it to meter and tell me. Nah, 0.0502. Okay. So okay. Now we need to find the induced EMF in the armature winding. So induced EMF is EA, which is equal to KA 5p omega m, right? So K you have to find. What is K? K is the machine constant. Already we discussed yesterday. What is K? Can you tell what is the equation for K? Huh? What is? 2 pi. Now you can find it, right? Just put the values, you will find K. 5p is given, omega m you can find, right? Omega m is also given, it is here, 183.2 radian per second, right? Okay. Now you substitute, you will find the voltage across the armature EA. Okay. So what is the voltage you got? यहाँ पे एक सीट खाली है, पीछे जो लोग बैठे ना प्लीज कम. So how much you got? EA? What is the value of K? First tell me K. What is the value of Z? You have to find. P already know. P is equal to 2. Z equal to how much? Can you tell? 24 coils, 18 turns. So 24 into 18 into 2. Okay. It is number of Z, the number of conductors. Okay. that is Z. So now you can find Ka. So what is Ka? Let us assume as it lap winding, so A equal to P, that is equal to 2. Okay. Please tell me the answer quickly. Which one?
That K, the final.
Ka.
Yes, sir.
137.5. Okay. Now you find Ea. That is voltage generated by the voltage induced across the armature. Huh? कितना आ रहा है? Then there is some mistake. Then why it will 136? Huh? K is how much? 68 point? 24 into 18 into 2, because each turn has 2 conductors. 137. Okay. Okay, so it will be 137.5. Okay. Now can you find Ea? Huh? 6? 632.00. 06. Okay. So this is in volt, right? Yes. How much?
1264. 126.
126. Okay. Okay, let us see. I will show you the answer also. Okay. Now coming to the B, induced EMF for coil. Huh? So you need to find number of coils per parallel path. Then you have to find the voltage across each coil. Okay? Because the voltage whichever we got, it is the voltage across the parallel path, right? We have 2 parallel paths like this. I have shown you yesterday also, right? We have 2 parallel paths, and this is the voltage EA. Okay. Okay, now we need to each parallel path, across each parallel path we have the voltage EA. Now we need to find number of coils per parallel path. Total number of coils we have is 24, right? So therefore per parallel path we have 12. Okay. Now I have to find EA by 12. How much it is coming? Yeah?
105.37.
Okay. Now see, C part is the induced EMF per turn. So each coil is having 18 turns. So divide by 18. Okay. So how much you will get now? 105, 18. 85. Now EMF per conductor. Each turn is having two number of conductors. Huh? So per conductor, what will be the EMF? 2 point something it will come, right? 5.85 by 2. 2 point. Now let us check the answer. This is your AP. Is it visible? Effective area, I think it is correct. What we found. 5P, it is correct. Okay. K is correct. Very good. All of you. Yeah. Then EA is correct. Okay. Then E coil is also correct, right? Then E turn is also correct. EZ is also correct. Okay. So I hope everybody understood this problem. This is a very simple, straightforward problem. Okay. Okay. So today we'll see force on a conductor. Okay. Because we talked about in the last class the torque developed. We have related this like last class that PD equal to TD omega m, right? So this TD is the developed torque in the armature and PD is the developed power in the armature. Okay. So therefore we related PD equal to TD into omega m, and this TD in fact we can derive in other way also, in alternative way. Last class we have derived TD equal to Ka phi Pia. Okay. If you remember, last class we derived this. Okay. Now in alternative way we can derive just by finding the force on a conductor when the loop or when a turn of a coil of conductor coil is placed in the magnetic field, and if the coil is carrying a current, then obviously the force will be exerted on the coil, right? What is that law? Which law actually acts here? Lenz law. Very good. Who told this? Very good. Lenz law. Okay. By which it is the law where we see that the force is developed on a current carrying conductor when it is placed in a magnetic field. Okay. So that is what we will read here. This we will study here. This force, it is a vector quantity, which is the integral of ideal cross product V. V is the flux density. This is the Lenz's force law. Okay, everybody, I hope you have read this in your class 10 or 11, wherever, right? Okay. So this is a conductor which is placed in the magnetic field. Now I can see the current is flowing in this direction, right? And now your force will be, it will depend upon the magnetic field. If the magnetic field is in this direction, then the force will produce in this direction. That is, sometime also we read this as Fleming's left hand rule, right? So Fleming's left hand rule is this, right? So if this will show the magnetic field, this is the current, this will be the force. Okay. So this F we can write ILV as magnitude and with a vector quantity that will show the direction of the force, Fi. Okay. Now if I find the effective force on a coil, because the coil has two sides, it is placed, suppose we have one turn of conductor that is placed inside the magnetic field, then the effective force will be twice of IVL, the magnitude of the force effective force on the coil. It will be twice of IVL, right? Then what will be the torque developed in the coil? That will be FER, right? R is the radius of the coil, okay, by which the axis at which the coil is rotating, right? Here in the machine, of course, we have the shaft, where the shaft, from the shaft to the coil outer surface is the radius, right? Now T becomes 2VILR, okay. Now this I can write in case of DC motor TC, that is torque developed on the coil. It will be twice BLR IC. IC is the current passing through the coil, okay. Then I can write the net torque developed in the armature will be torque developed by 1 turn into total number of turns. So what is the total number of turns? We have seen yesterday, that is CNC is the total number of turns, because C is the number of coils and NC is the number of turns for coil. So therefore total number of turns is CNC. And now each turn is developing a torque, that is 2VLR IA by I. IA by A means that is the current actually flowing in the coil. That means your IC is equal to IA by A. IA is what? IA is the armature current which is actually we see outside, which is coming after the commutator, that is IA, okay. So IA is the armature current which we in fact at the load side we measure, right? So many of you have experienced today also in the lab many of you have done today and yesterday how to measure the current, how to see. Those who have performed specifically DC generator experiment, they might be knowing this is armature current, means what we measure at the external circuit, right, when the load is connected, okay. Now IC is your current inside the machine which is flowing in the coil and which is equal to IA by A, right? So A means A is your number of parallel paths, okay. So now we can just multiply it, we will find BL, L is the length of the machine, BLRZ by A into IA, okay. Now we know the surface area, now also we did in the problem, surface area covered by the pole. So that is AP will be equal to twice pi RL by P, okay. Now I can substitute, instead of B I can substitute phi P into A, or I can say phi P into AP. Phi P is your flux per pole and AP is your surface area of each pole. Now surface area of each pole is here we have found 2 pi RL by P, which I can substitute here. After substituting, I will find the torque developed here in this equation. Finally, I will find K phi P IA, which we obtained in the last class also, right? Is it matching? Yes. So K is nothing but PZ by 2 pi A, right? So I hope everybody understood this. Okay. Can we move forward? Okay. One more problem. Okay. Same problem, a little modification. Problem is same. We'll not do now A, B, C part. Okay. Remove this part. We'll remove. Just do the blue color part, which is if the armature current of the machine in this example, in the above example is 25 ampere, determine the current in each conductor, the torque developed and the power developed. Please do it quickly and tell me answer. Very easy problem. It is also a straightforward problem. Okay, let us see the answers. Current per conductor is 12.5 amperes. Huh? Okay. And TD is your 171.89. That is correct. Straightforward. And PD is 31.49. It is also correct. Okay. Okay, so I hope it is correct, but only the current for conductor is not correct, so please rectify it, okay? I hope everybody understood this. Okay. Now we'll go to a next topic of our discussion, that is magnetization characteristic of a DC machine. Today I hope one of the group performed this experiment of plotting the magnetization curve. Which group did this? Please raise your hand. Anybody did this today? No? Huh? So magnetization curve means we draw the open circuit characteristic. Okay. So what is this magnetization curve or magnetization characteristic of a DC machine? So we know that induced EMF in the armature winding of a DC machine is directly proportional to the flux per pole and the armature speed. Already we have seen, right? EA is equal to K phi P omega M, right? And therefore EA is your, which is directly proportional to phi P, and also EA is directly proportional to omega M, right? If I will run my machine at the rated speed, let us say omega M is constant at rated speed, and I am varying the flux. How I can vary the flux? If it is a permanent magnet, we cannot vary. I told you in the beginning, because permanent magnet always gives the fixed flux. So when we connect an electromagnet to the field, then we can vary the flux by changing the field current. Current to the field we can change, right? So then let us assume the field winding of a DC machine is connected to a variable DC source, and that is capable of applying a desired field current. Okay, there is a maximum limit of the field current we can actually supply to the field. So what is the maximum current we can supply to the field? Yeah? What is the maximum current? If it is sound generator, we can give actually EA by RF. Okay, RF is the resistance of the field circuit. Okay, that much of current we can only supply. If we go beyond this, then it will become overheated and it will burn. Okay, so therefore it is mentioned the desired current we should give up to maximum level, not beyond that. If the armature circuit is left open, that means it is open circuited, and the armature is rotated at rated speed, the machine, then the induced EMF in the machine can be expressed as this. Okay, because the speed is constant, so now your EA will become K1 phi P, another constant, because K1, where K1 is equal to Ka omega M, which is another constant, because omega M is constant here. Okay, now what will happen to the magnetizing characteristic? So phi P equal to Kf If. We know this because your flux will depend upon the MMF. So MMF will depend upon the current, right? MMF, we know MMF is magnetomotive force, which is NF If, right? Okay. And the flux, the production of flux in the field will depend upon the MMF. So therefore I can write phi P is equal to Kf If, right? And hence I can write EA is equal to K1 Kf into If, right? So your EA, that is the voltage induced if the load is not connected to the outside output end, right, to the armature. That means it is open circuited. If we'll put a voltmeter, then we'll measure EA. We call it open circuit voltage. Okay. So EA will be nothing but it will be equal to K1 KF IF, right? Now if I'll plot this EA, that is induced EMF, versus the field current, that will give me the magnetization characteristic. But now the question is, why this magnetization characteristic is looking like a curve? Why it is not a straight line? Because of the hysteresis, effect of hysteresis. Already you know the BH curve, right? Hysteresis loop is being formed. You know BH curve, everybody I hope already studied, right? The BH curve, if we plot B and H, it will be like this. Then I will reverse, it will be like this, right? So, but only we are considering this part, right? This part only we are considering. We are focusing on this part. We are not going reverse and again going again in the positive direction. Only we are considering this part. But again now the question is, why it is not starting from the origin? Why it is starting from here? Here. Why it is not starting from origin? Because there is a residual magnetism in the field before, because as it is continually being used, so it has a residual magnetism in the magnet already, right? So when we start exciting this, before starting also it has certain residual magnetism. So therefore as soon as we run the generator, there will be certain EMF. We call it residual voltage. Okay, and that residual EMF is because of the residual residual flux, right? So this is your residual voltage EMF, and this residual EMF is because of the residual flux in the magnet or pole, right? So as soon as we give excitation, it will gradually increase, right, with a linear mode, and again after certain time it will become saturated and it will become a curve, right? Okay. So this is your air gap line, what we have plotted from origin. What this air gap line indicates? This air gap line indicates that if instead of core, ferromagnetic core, if we consider this air as the medium, then we will get this kind of curve, straight line. Okay. So then why we are not considering air as a medium? So we could have made air, right? Just put the coil in the starter, that will produce the flux. Why we put this ferromagnetic material? And over the ferromagnetic material we wound the coil, right? What is the point?
More flux density as compared to air, we have more flux density in the ferromagnetic.
Why we get more flux density? Because
Dipole, the poles align according to the...
No, because of the reluctance. Okay?
Yeah.
Because the reluctance of the air, medium air, is very high as compared to the ferromagnetic material. So therefore we will not get the flux density. The flux density will reduce if we use air instead of ferromagnetic material. Therefore this is, even if we are getting a curved characteristic, but we prefer ferromagnetic material over air because it will produce more flux density, and by that way it can link more flux to the armature circuit. Okay, now we can see here that if your flux remains constant at some point, then your speed is proportional to the EMF, right? So if we'll see your EMF is proportional to the speed, then considering this relation we can find this relation, right? EA2 is equal to omega M2 by omega M1 into EA1. That means at a different speed we can find different EMF, right? Suppose one speed and one EMF is given to us. Suppose let us say EA1 at omega M1 is given to us. Now if I'll ask you to find omega M EA2 at omega M2, then you can find using this formula, right? Because they are directly proportional. The speed is the EMF is directly proportional to the speed, right? So this kind of relation we got from here, this magnetization curve, right? But this is only applicable, we should remember, only when the machine is operating in the linear region, okay? If it is go beyond the linear region, if it is going to the saturation region, this relation may not hold true. It will not hold true. And even the relation of EA directly proportional to phi p, this will also not hold true. Okay. Okay, now we'll little bit discuss about commutation, theory of commutation. What do you mean by commutation? Commutation means changing the direction, right? When the current direction changes in the armature coil, we call it commutation. So we are talking about a DC machine, but we are talking about again change of direction of the current, right, in the coil. We know in the AC circuit there is a change of direction of current, right? When AC load is connected to AC source, every time the direction changes, right? Every alternative cycle, the direction of current changes. But in case of DC circuit, it is unidirectional, right? But here, theory of commutation applies because the current changes in the conductor when the conductor changes its position from north pole to south pole, from south pole to north pole. So under north pole, in which direction the current is flowing, it may actually change, it will change when it is going to the south pole, right? And this transition happens in the commutator, before the commutator, okay? So for the successful operation of a DC machine, the induced EMF in each of the conductor under a pole must have the same polarity, right? And if the armature winding is carrying the current in each conductor under a pole must be directed in the same direction. As I told, it will be unidirectional till the conductor is placed under one pole. And as it moves further, okay, from one pole to next, then what will happen? There is a reversal of current in that conductor. Okay. So the conductor and thereby the coil in which the current reversal is taking place are said to be commutating. Okay, commutating. Okay. So the process of reversal of current in commutation coil is known as commutation. This is the commutation process we can see here. Okay, here the current in one coil, that is IC we are seeing here, right, which is actually IC, the magnitude is IC. Now when the conductor moves to the next pole, right, to the south pole, we can say from north to south pole, it will actually shift its direction to the negative direction, right? Okay. But now the question is, will this happen instantaneously? Will it happen instantaneously or it takes some time to happen? Huh? Instantaneously will happen, the change? It will not happen instantaneously, because why it will not happen, I will show you. Huh? No, because it is an inductive coil, right? So change in the current in the inductor instantaneously. Can we change current in inductor instantaneously? No, we cannot change, right? Because it is an inductive coil, so it is not possible. And also another factor matters, the cross contact with the commutator segment. Okay, so we'll see We'll see how it happens. So it will take time, certain time, and that time is Tc. So we call this commutating time. Okay. So this commutating time plays important role. If we can make the commutator segment infinitesimally small, then we can get very less value of commutation time. But it is difficult to achieve because we cannot go beyond certain size of smaller, right? If we can make it very small, infinitesimally small size of the commutator segment, then this time will reduce, right? Why it will reduce, I will show you here. What you are seeing here, a two-pole machine, right? Here we have north pole, here we have south pole, right? And we have various coils, different coils, A, B, C, D. They are marked as A, B, C, D, E, F, G, H. These number of coils we have, right? Now here these are the commutator segments. They are marked as 1, 2, 3, 4, 5, 6, 7, 8. We have 8 number of commutator segments, right? Now I have two brushes. One brush is A and the other brush is B. Okay. Now what we are observing here, suppose we will consider coil B, let us say. Okay. So now in coil B, the current is in this direction now, right? Let us see next picture. Okay, here the coil B has current in this direction, right? Now the coil B moved to this position. What will happen here at this position? This is the neutral plane, because when the conductor or the coil comes through this, there is no linkage of flux. That means there is no induced EMF. Therefore, there will be no current at this position particularly, right? And then as soon as it will move, again it will have current flow in the negative direction when it comes under the south pole, right? So as soon as it comes under the south pole, there is a current flow in the negative direction, right? So that means there is, in order to change the current direction, it is taking certain time, right? Because it is passing through this position, and here it is actually the current direction is changing. Okay, it is not instantaneous, and also the inductive effect of the coil, it also taken into account, right? Now when it will move again further, okay, so again when it will move further, the current direction will be in the negative direction, right? Okay. So this is the process of commutation, what we saw, right? Okay, so we'll stop here, and next class we'll see. Okay.